Well, I cannot bend spoons with my mind, but I can bend G-code with my newly developed non-planar 3D printing method. Let's find out more. Guten Tag everybody, I'm Stefan and welcome to CNC Kitchen. A part of this video is supported by Brilliant. Let me quickly tell you a story of how I came up with my non-planar 3D printing idea. Some of you might know that I've got an adorable 1.5-year-old daughter, and as a caring dad with a 3D printer, I of course wanted to print something for her. The idea was to make her a ball run that I can easily attach to a window. The tube sections I wanted to make are pretty tall parts, and I'm usually impatient and want quick results. Printing high parts conventionally often takes quite a long time. So I use the spiral vase mode when I usually print vases or stuff like that. Here the printhead moves in a very shallow but a continuous spiral around the outside of a model. This is great because it's quick, but it also leaves you usually with pretty tough parts. Designing parts for vase mode is an art, and I'm always super impressed if RC airplane designers like 3D Lab Print manage to create whole airplanes that can be printed in a single closed contour with barely any travel moves to minimize oozing, so you can print them with lightweight foaming PLA. I did my best and tried to at least design a bit more complex parts for spiral printing by adhering to some simple rules. I'm not a great designer, but the results could be worse. The pieces for the ball run all have grooves in the back in which cheap suction cups attach so that I can stick everything to smooth surfaces. Links to all of the files are down in the description, and if you'd like to know more about designing for vase mode prints, let me know in the comments and maybe I can make a small tutorial. Anyways, the problem with this method is that you're limited in the shape of your designs because you always need a closed contour and a flat top and bottom surface. So printing just pieces for my daughter's ball run, where the beginning and the end are parallel, would be boring. That's why I got the idea in my head to just bend the G-code of one of these straight sections and make them curvy. To do that, I wrote a small Python script. Accomplishing that wasn't hard, and I was able to reuse a bunch of Python code I still had from my gradient infill method I developed a bit back. The idea was to define a spline with at least 2 points and set the starting angle perpendicular to the print bed and the end to how much I want to bend the pipe. Then I take every movement command in my G-code, move it onto the spline and tilt it by the angle of the spline at that point. If we do that for all of the commands in our G-code, we get a bent model in the end. Of course, we need to adjust the flow because layers get thinner on the inside of a bend and on the outside they get thicker. So I just recalculate the local layer height for each section and scale the flow. Then I need to account for the fact that the spline is of course longer than the initial perpendicular axis if it goes to the same z height, because otherwise the final part would be stretched. There isn't a pretty user interface at the moment, and I just set the name of the G-code file, define the spline so that's in the center of my part, has the desired shape, and hit run. After a minute or so, the script will create a new G-code file with the morphed and band commands. Having ideas like this and then implementing them nicely brings me to today's video sponsor Brilliant. Brilliant is a problem-solving based website with a hands-on approach to learning. They offer over 60 interactive courses in math, science and computer science. I'm super happy that they support this video because their approach to learning is something I wish I could have had when I still was in school or university. The thing that I enjoy about Brilliant so much is their interactive learning approach. I'm not good at learning just from reading a book or watching a video, but with Brilliant's interactive courses, where you're constantly challenged with questions, games and exercises, learning, understanding and applying new concepts becomes so easy and enjoyable. Brilliant makes sure that you're not getting lost and provides step-by-step solutions if you're struggling with a topic, so that you can learn everything to achieve your goals. So if you want to refresh your knowledge about trigonometry, just as I had before creating my G-code bending script, or how to program in Python in the first place, Brilliant has got you covered. I also recently took a course in neural networks and now finally understand the concepts. I really like learning hands-on, and if you are watching this video, I'm pretty sure you'll enjoy Brilliant just as much as I do. I highly recommend trying it out for free, and the first 200 people who use the link in the description will get 20% off their annual premium subscription. Thanks to Brilliant for sponsoring this part of the video. So let's look at our results. G-code viewers seem to have a bit of a problem displaying the results, so please be aware that some lines look a bit strange. And just that simple, we have created non-planar G-code, where the printer continuously uses all of its axes in a significant way, instead of just stacking individual layers on top of each other. That makes the printing process look really mesmerizing, and the final parts look beautiful, especially with a dual extrusion filament. My code still looks horrible, but I've of course shared it on GitHub for everyone to look at, use and edit it. It's a bit buggy and limited, but it even works with regular slice parts like this 3D Banshee or my mini Stefan. The bend parts look super smooth, with dynamically changing layer heights with thin sections on one side and thick ones on the other. You might have already noticed it, but non-planar printing comes with its own challenges. If you don't have a way to tilt your print head, you are quite limited in the slope that you can print. Most obviously, there's clearance. I first started printing on my Prusa, but quickly noticed that the fan shroud and the bed sensor are so close to the nozzle plane that barely any non-planar printing is possible. I quickly switched to my E3D tool changer, where I have a volcano tool installed that I turned by 90 degrees so that its thin side is in the non-planar axis. I also removed the silicone sock because even that was in the way. And most importantly, the nozzle itself has a massive impact on the angle printing capability. E3D's nozzles have a pretty short tip, and the 7mm hex stands out quite a bit. Therefore, I installed a CHT nozzle on my Volcano heater block by using one of our Volcano adapters, now available over on cnckitchen.store. They bridged the length difference to a Volcano nozzle and let me use any of my old V6 nozzles on a Volcano hot end. Pretty cool. The new nozzle and the adjusted part cooling shroud gave me quite a bit of room for angled printing. These were the challenges on printer level, but even the tip geometry of your nozzle limits what you can and can't do. If the tip is too wide and the layers too thin, you will at some point start plowing through your already printed material. And I had quite some failures until I determined that everything above around 30 degrees angle isn't really doable with my setup. Still, I was able to print an assortment of bent tubes and pipes for my daughter's ball run, which are quick to print, look better, and due to the bend are more versatile. I'm not the first one who came up with the idea of non-planar 3D printing. There is a 2015 patent from Autodesk on a method, and I'm sure you have seen videos about Daniel Ahler's Slick 3R implementation of non-planar slicing. It can produce some really nice top layers, but is very limited in that it only works on the upmost surfaces of your part, and getting it to run in the first place is challenging on its own. Then there is René Müller's slicer that segments a print into different regions and then prints different sections at an angle, which allows printing horizontal overhangs without any support structure. And a 4 or 5 axis print head allows for even more complex printing. This is a fantastic proof of concept, but is currently very limited due to the segmentation process. Full control G-code is another way to do non-planar 3D printing, but here you don't slice an STL, but program your G-code manually with mathematical functions. Great for artistic parts and niche applications, but not the next non-planar slicer. There are even more examples of non-planar 3D printing with multi-axis CNCs or robot arms that are commercially available. Still, besides not being something for home users, these aren't usually processes where you load in your part and automatically get working code. This nicely illustrates the problem with non-planar 3D printing. Hardware isn't the problem, because all our 3D printers can easily run all of their axes simultaneously. The big problem is software. Regular 2.5D slicing is super easy. You slice your STL with a plane and get all the perimeters, which get then filled with 2D moves. Doing that for each layer and just lifting your nozzle after each one gives you your final part. No risk of crashing the nozzle, no challenge of sectioning your part or identifying surfaces that could be printed in a non-planar fashion. This is why even commercial software still struggles with complex geometry and why there is no easy open source solution at the moment. It's just complex and complicated. My approach is definitely no rocket science, revolutionary, or the perfect solution for all of our non-planar desires. Yet I think it's an idea that can have potential for some applications because it uses a conventional slicer and then just modifies the G-code a bit. I'm currently just bending my G-code on one plane, but you could easily do that in 3 dimensions or just use a mesh over the whole print volume and use interpolation to deform the whole printing space smoothly. I personally don't have the time and skill to do that myself, but I'm good at communicating ideas. So if I inspired you, please go ahead and make something really cool out of this idea. And everyone else, please leave your thoughts and ideas down in the comments. And if you enjoyed this video, hit the like button and consider subscribing. Thanks for watching everyone. I hope you found this investigation interesting. If you want to support my work, consider becoming a patron or a YouTube member and check out the other videos in my library. I hope to see you in the next one. Auf Wiedersehen and goodbye. With mathematical functions.